ahead and get started. If you get your notes out, we'll start rolling. Chapter 5 has a lot of stuff in it. I wish they would have split it into smaller groups, but hopefully we'll be able to get through it and be okay. First thing we're going to talk about is chemical reactions. Actually, before we actually get started on this, come on, why are you not moving forward? Remember that long paper that I gave you? The map of how to know and name all elements. I want to go over that and have you fill that in. So the first thing that you're going to do is that big long map. Did everybody get one? If you didn't, there's some more over here, but it looks like this. Map of how to know, how to name all types. That looks like this. Does everybody have theirs out front? Okay. We're going to fill that in today. This is a good review sheet that you would want to keep with you till the very end. If you don't have one, there are some over there. So the first thing you want to ask is the first element, a metal? If it is, if the answer is yes, then is it a metal in the first two columns or in the slide? Remember the slide is boron, aluminum, gallium, zinc, or silver. These are ones that have specific charges. So you want to say, does it have a charge I know about? Okay, that it doesn't have a different charge. So if it is, the answer to this is yes, that's where the first element is, then remember those are the ones we know the charges of. We don't have to list them. We just name the first element and name what it's with. We also balance the charges so that they add to 0. Okay? But the charges are known. We know them. If the answer to that one was no, then we've got type 2, what I call type 2. This is where we are in the P, the lower P, the D, the F. Okay, and you can put more stuff than what I've written up here because I'm giving you more stuff. So this is going to be your map to remember things. So type 2, we don't know the charges. We have to be given them in a Roman numeral, or we have to be able to figure them out by having them combined with something we know the charge of. But either way, both of these types, type 1 and 2, we are still trying to balance the charge and make it equal 0. So we say, I need this many of this element and this many of this element to be able to add together and equal 0. If we go back to the first question and we say, is the first element a metal? And we actually say, no, it's not a metal. And we say, is the first element hydrogen? Well, if that's a no, actually, yep. If that's a no, then I've got to have type 3, which is in the upper block of the P. And I'm going to, after I get this up, I'll let it sit for a minute so you guys can get it down. This is where we use the prefixes, the mono, di, tri, tetra. We don't worry about the charges here. We just tell how many of each element we have by using mono, di, tri. Remember, we don't use mono on the first element, but we do have to use it on the second. If that first element is a hydrogen, then we have an acid. That's type 4. And if that acid starts with the word hydro, that hydro gives me a little cue here that it's just 2 elements, hydrogen and one other element. So it's going to be hydro, whatever the hydrogen's with, ic and acid. That's how we're going to have it, it's going to be named, or that we need to name it if we're given the acid. If that acid does not start with hydro, no hydro, then hydrogen's with a polyatomic. And if that polyatomic had an 8 ending, then we change it, Thanksgiving dinner, 8 goes to ic and we add acid. If that polyatomic ended in ite, that means we were going in a fight, OS, we're going to get in a fight in an acid situation, so we change it to OS, an acid. Or if they gave us the acid, chloric acid, then we would take and say, okay, it's with a hydrogen because it's an acid, that's my positive, and I look for the chlorate, or I try to remember what the chlorate ion is. If they gave me sulfurous acid, I would look and say, okay, sulfurous came from sulfite. I'm still going to put it with a hydrogen ion, but I need to remember what sulfite is. And remember, sulfite is 1 less oxygen, so it's SO3, has a -2 charge. So I need 2 hydrogens to balance out the charge. So still with the acids, I am balancing charges, but I'm just adding however many hydrogens I need so that it will add to 0. I'm not changing what it's with. I'm just changing the number of hydrogens I have. So this is just a quick map of how to name all the types on the periodic table. And hopefully that will help you as you remember down the line, because you're going to need to keep referring back to this, even in this section that we're going into. So if you are struggling with the last section, please come in and get some help with me so that naming and writing formulas becomes second nature, because that's what you need to have it do. Yes?
What does it say, like, at the end of the type 3 one?
So prefixes on each element tell the number of each element. It's supposed to be element. The number present, I think, is what it says. Number present of each element. But I didn't put of each element on the end. So like N2O5 would be dinitrogen pentaoxide. That tells me how many of each one's present. Looks like there's still a couple head bobbers, so I'll leave it up just a minute more. Remember that you can add to this map however it helps you to remember things. If you've forgotten your Roman numerals, you can add your Roman numerals there. You can tell you type 1, our column 1 is +1, column 2 is +2. Boron, aluminum, gallium are +3, zinc's +2, and silver's +1. You can do that. You can add in type 3 the prefixes mono, di, tri, tetra. So you have everything in one spot that you can go back and you can look at, and you have a map to be able to name or go backwards and find the formula. So type 4, 2, and 1, you have to balance the charges. But type 3, you do not have to worry about charges. I will put this up on the website or on the Canvas so that if you want to go back over it, you can. Every day I do that, so please feel free to do that. I've been putting it up on YouTube because it's a lot easier. If you get onto YouTube, then you can follow the channel, and every time I put a new video up, it's there. Okay? All right. Are we okay to go forward? I'm not seeing as many head bobs. All right. So this chapter starts with introducing chemical reactions. And we've already done the chemical physical lab. So you should be able to tell me what the difference is between a chemical change and a physical change. Does anybody have any ideas? Okay, so like physical change would be like cutting bread. It's still bread. I haven't done anything except make the shape of the bread different. Okay, or cutting a log. All I've done is physically alter the state. It's still the same stuff. So if I take ice and I melt it, it's still water. Whether it was ice or water, or if I heat it up and make steam, it's still water. So that's a physical change. If I take logs, which are mostly cellulose, and I burn them, I'm going to get ash. That's something new. Because it's something new, that's a chemical change. So in a chemical change, we're breaking bonds of the reactants, we're reforming them and making a new product. But we're not changing what we have there. We're just changing the order they're arranged in. Okay? So chemical change or a chemical reaction converts one substance into another. We're breaking bonds of the reactant and forming new bonds of the product. So instead of having a cellulose, which is a very long structure, over here I end up with carbon products. Black is the carbon itself. Okay, so writing chemical equations, we need to know what's on what side. So on the left side are the reactants. On the right side are the products. The coefficients help us to know how many of each we need. So here we have methane plus 2 oxygen yielding carbon dioxide plus 2 waters. So again, on the left is your reactants, on the right are your products. And you'll be able to pull those out. Okay to go forward? Okay, so law of conservation of mass basically says I can't create or destroy matter. Matter is there. I can rearrange it, but I can't create or destroy it. So coefficients in a balanced equation are put there so that we have the same amount of an element in the reactants as we do in the products. So we're talking about the number of atoms of carbon present in the reactants and the products. I can't lose some carbon along the way or gain some carbon along the way. They've got to be the same on both sides. Okay, moving forward. This is a chemical equation. I put a visual up here for you so you can sort of see what's going on. This is methane and oxygen going to water and carbon dioxide. Well, as we look at the reactants over here, and we look at what's here on this side, we have one carbon atom. On the other side, we have one carbon atom. So that's okay. If we go to the next one, which is hydrogen, over on the reactant side, we have 4 white. And on the product side, we have 2. I have to have the same amount. So I have to put another water over here so that I can get 4 hydrogen atoms. Okay, then I go to the next one, which is oxygen. Oh, I put the 2 in front in the equation so I show that I have 2 water molecules. On the oxygen on the left, I have, or on my reactants, I have 2. On my products now, I have 4 red blobs. So I need 2 more oxygens to come in, and they come in pairs because they're part of the diatomics. So if you look there, I have 2, so I need to change that to 2 oxygens. I have the same number of atoms on my reactants as I do my products. That's because of the law of conservation of mass. This is known as a balanced equation. Okay? So I want you to grab 2 colors. I don't care which they are because we're going to make this quick. I want you to color on that grid that you have. Reactants, 1 color. You can just go all the way down in the scribble, in that thing. Just scribble that color there, all the way down in reactants. Whatever color, doesn't matter. Just scribble it down. In the column that says reactants. Okay, scribble the other color in the one that says products. Okay, so I'm going to use blue for my reactants. And I'm going to do red for my products. And I can spell, really, I can. So, easy way to do this is the arrow always points to the products. So, I'm going to grab my product, and I'm just going to go down, and anything that is the arrow's pointing to, I'm just going to circle, because that is my product. Then I'm going to grab my reactant and do the same thing, but on the other side. So the arrow does not point to the reactant. That's what I start with. And I'm just going to circle this all the way down. Makes it a lot faster than just rewriting them. Okay? You just need to be able to identify which is the reactants and what are the products. That's not a hard thing. Okay? Anybody have problems with that? All right, so we're going to go forward. Again, remember, arrow points to products. So, equations are said to be balanced when matter is conserved. So, what we're going to do now is I've got some little scratch pieces of paper. I'm going to pass them out, grab a few of them. Thank you. It doesn't matter how many you got. If you don't use them this time, you can use them next time. I like to have a blank piece of paper, a scratch piece of paper that I put underneath an equation that I'm trying to balance, because oftentimes they're smashed right next to each other. This is what I do. I have to remember that a reaction is like the end of the year. And at the end of the year, Santa Claus comes and he says, ho, ho, ho. Okay? So I remember hydrogen second to last always, oxygen last when I'm balancing. If I remember that, I can balance anything else before that, but hydrogen has to be second last, oxygen very last. Then the reaction will balance a lot easier. Okay? So in this one, This one's an exception into the rule, but that's okay. We're just going to do it. Underneath the arrow, so line up your paper, or you can, I think I gave you enough room on this one. You can just do it on your paper. We'll save those papers for later. Just put H and O, because that's the only thing that's in here. I'd underneath the arrow. And then I look on the left side and say, how many hydrogens are on the left side? 2. How many hydrogens are on the right side? 2. That's balanced. We're okay. Keep going. How many oxygens are on the left side? How many oxygens are on the right side? Okay, now I have a problem. It's got to be the same. So the only way I can change that is if I put a 2 right here, then it times this through. That changes the oxygen to 2, but it also messes up my hydrogen, changing it to 4. You see that? So now I got to go back up and balance my hydrogen. Well, that's easy. I'll just put a 2 here, and now it's 4, and it's balanced and done. Okay? So let's go to this next one. Again, leave hydrogen and oxygen to very last, so it's going to be a CHO. And on the left-hand side, I've got 1 carbon. On the right-hand side, I have 1 carbon. On the left-hand side, or reactant side, I have 4 hydrogens. On the right-hand side, or products, I have 2. So again, I'm going to put a 2 up here, change that to a 4. On the oxygens, this is where it gets tricky. I've got 2 on the reactant side, but I have 2 plus another 2 on the reactant side, giving me 4. Well, that's pretty easy to fix too. I'll just put a 2 here. That changes it to 4, and I'm balanced. Okay, we're going to get more tricky as we go along. Over here, I've got iron and chlorine, no oxygen or hydrogen. Okay, on the left-hand side, I have 1 iron. On the right-hand side, I have 1 iron. On the left-hand side, I've got 2 chlorines. On the right-hand side, I have 3 chlorines. Okay, what's a common factor between 2 and 3? 6. So if I put a 3 in front of this, then that will make it a 6. And if I put a 2 in front of there, that will make it a 6, but it messed up my iron and made it a 2. So I'm always looking back when I have to put a number in front. Well, did it mess anything up? I already balanced. So I'm going to have to go back and put a 2 here so I can balance my irons. Okay, here we have another CHO. So CHO. We have 3 carbons on the left, 1 carbon on the right. So I'll put a 3. Hydrogens, 8 on the left, 2 on the right. What do I need to do? Put a 4 to make that 8, right? 4 times 2 is 8. On the left, I have 2. On the right now, this is where it gets tricky again. I've got 4 times 1 is 4, plus 3 times 2 is 6, giving me a total of 10. So over here in front of the oxygen, I need to put a 5, because 5 times 2 is 10, and I'm done. Okay, everybody okay so far? Okay, now we're going to get really tricky, actually, after we do this. Okay, so you need to know some symbols, some basic symbols. So an arrow means a reaction's taking place, and I'm going to get a product. A delta means I've applied heat, so they usually put the delta above the arrow. And S means solid, L means liquid, G means gas, AQ means aqueous. That means that I've dissolved it in water. So most of the chemicals we've used in lab are aqueous. We've dissolved them in water. Okay, and you need to know those. So if you don't know them, write them down because there's some blanks on your chart. Most of them are pretty straightforward except for the delta. You just need to know that one's heat. S solid, L liquid, G gas, AQ maybe might be new. Okay, so now we get the tricky stuff. So on this one, I'm actually going to bring up a scratch piece of paper, and you'll want to use one of those papers that I gave you so that you have so here's my blank piece of paper I'm going to put underneath. This one gets a little hairy, so let's look at this. This one you have to use a trick, and I'm going to teach you the trick. So it is a CHO also. On the left, how many carbons? 6. How many on the right? 1. So I know I'm going to have to fix that by putting a 6 here, change it to 6. So you're doing this on your little scratch piece of paper underneath. And I just put it right underneath the equation, so it's right there, and I don't have to keep looking back and forth. Over here I have how many hydrogens? 6. How many on the right? 2. So I need 6. So 2 times what is 6? 3. So I now have 6. Oxygens, I have 2 on the left. Now this is tricky. Over here I've got 3 times 1 is 3, plus 6 times 2 is 12, giving me 15. Okay, but I can only get even numbers on the left side. So we're going to use a trick. And this is a trick that I use so that you don't have to sit there and try and figure out what you need to change everything to. If I take this side, and just for a second, because I can't leave it that way, times it by 15 halves, then I'll get 15 and it'll be balanced, right? So I'm just going to put that there just for a second. And then I'm going to use my math brain and say, okay, if I have a fraction in a formula and I want to get rid of it, what do I do? Times it by the bottom number, right? So I've got to times that whole equation by the bottom number. So this becomes 2, this becomes 15, this becomes 6, and this becomes 12, and I'm balanced and done. Okay? So if you end up with an odd number on one side and an even number on the other side and you can't get anything but even on one side, this is what you want to do. Okay? Now, I'm going to have you guys practice the others on here. I'm going to pull you by name up to do a specific one. So I'll give you a few minutes head start and then I'll tell you which one you're doing. So work on 2 through 8 right now, 2 through 8. Okay, Jace, I'm going to give you 2, Sierra 3, Kira 4, Kayla 5, Jaden 6, Isaac 7, and Noah 8. Don't feel bad if you didn't get one because there's another page. If you need help, let me know. as you finish yours, go ahead and put it up on the board. If you need help, let me know. Yep, this one's not. Oh, is that the numbers?
Yeah,
Okay. Hydrogens are off. You have 4 here and 2 here.
Oh, wait, so
Oh, and 2 there. Never mind, 4. Okay, yeah, you're good.
maybe you can help me with this?
Okay, this one's a little tricky. But number in the space, just leave it empty. So this is a tricky one. So over here you have 2 and 3 is 5, right? And over here you just have 2. So you're going to times this by 5 halves and then times everything through by 2. Yes. Okay, so we've got waiting for 2 more up front. Yep. Okay, go ahead and put that one up. Okay, like I said, this will be up on Canvas, so if you want to do them on your own and then go back and check and see if you got them, that would be great. Do we have any that anybody disagrees with? Let's do that first. You better not say the first one because I showed you that one. Other than we don't write ones, so that wouldn't be there and that wouldn't be there. I think we're okay. What do you guys think? Yes. Do you have another one that you're questioning?
Number 5, I thought they were like 7 and
Okay, on this side we have 6 plus 2 is 8. We have 2 plus 6 is 8. Okay, it's all right. If we need to go over some, let's do it. If you don't agree with them or think something's wrong, I might not have caught it either, so it's good to always double check. Okay, any others that you'd like to go over? You need the keys? Where did I put them? It's the gold key, little gold key. All right, let's go to the next one. I want you to try, let's try to go to the next one. There we go. Okay, I'm going to give you different ones. So I'll give you a few minutes to try them on your own. So we're just going up through 15. Did I give you more than 15 in your notes? I can't remember. Nope. Okay. Okay, Jacob, let's go 15. Calvin, 14. Noah, 13. Isaac, 12. Jaden, 11. Kayla, 10. Kira, 9. I'm going to make you change color so we can pop it. I gave you an easy one. Uh-huh. She says, yeah, it's pretty easy. Mm-hmm. Yep. Okay. So, do we have any that we disagree with? I think you guys did a pretty good job. The only one I see, nope, and it's not an issue. Okay, good. Way to go. You should be able to balance any equation that I give you. Okay, just remember that little trick for the ones that end up weird. They usually, for the most part, are ones that have plus oxygen yielding something. Those are the ones that sometimes can need that extra little tweak to balance it. Okay, so I'm going to go through the next part really quickly because we actually are going to cover it again on Monday so that you'll see it again on Monday in class. So I am going to go through it fairly quickly. So chemical reactions. We've got non-redox, that is double replacement, or called metathesis, and we've got redox, okay, which would be a single replacement, a combination, a decomposition, or a combination oxidation reduction, or combustion, sorry. So there's a sort of a breakdown here on what's going on. We're going to go into each of these a little bit more, so don't freak out that you don't know what these are yet. And there's a lab I really, really, really want to do, and we might just do it as a group and not worry about any write-ups or stuff next time, just so that you can see, because it's pretty cool. And it does show redox. Okay, we okay to go forward? Have we got all those down? No? Shaking heads? No, not even. It's really easy for me to write it down. All I do is click it. Okay, that sounds like a click it or ticket. Okay, going forward, let's talk about each one of these. So, a combination reaction is synthesis or addition. You actually take sodium metal and chlorine gas with a spark in between and you make salt. There's a YouTube video that you can actually look at, I didn't put it on here, where a chemist makes salt, fresh salt, over freshly popped popcorn. And he salts it and eats it. I don't know if I'd be that brave, but he said it was good. So they're separate, and then you put them together. So 2 or more elements that combine to become one. That's what synthesis or combination are. Another way to look at it, putting it together. Well, you know when sometimes you put things together, they fall apart. So if they fall apart, if you have one thing and it falls apart to 2 or more things, it's decomposition. So decomposition, when one thing falls apart into 2 or more. Okay, you can look at it several different ways. There's several different ways it can happen. Now, we used ammonia, which was on the bottom, ammonium hydroxide. The gas that was coming off was ammonia. What was left in the beaker, if you leave it overnight, is just water. So, because the ammonia goes off. So in order to keep ammonium hydroxide well, you have to keep it in a closed container. So, all right, so that's decomposition, falling apart. Then we have single replacement. Single replacement reactions can happen with the positive ion or the negative ion. So I've shown both of them here in a dating kind of situation. We have Fred and, is it Wilma? And then, I can't remember the other girl's name. Anyway, she comes in and switches places with Wilma. Or we have the guy down at the bottom that cuts in and the other guy gets kicked out. So single replacement can replace either the positive or the negative ion. Then we get double displacement or double replacement, and this is where you have 2 couples that they switch partners. Okay, so if I have an acid-base or strong acid-strong base reaction, then I'll end up with water. OH hangs together, and if I put an H with it, it becomes water, HOH. H is an acid, OH is a base. These are also called metathesis. Don't ask me why, that's just the other name they have. So looking at it in more visual form again, 2 couples, switch partners, 2 couples, switch partners. So double replacement. Summary of all the types we talked about so far. So synthesis, combining, decomposition, falling apart, single replacement, one person gets replaced. It could be the girl or it could be the guy, so the positive or the negative. Double replacement, we just switch partners. And then the one that all high school kids like is combustion. You take 2 things and you light them on fire, and you get water and carbon dioxide, off for the most part. There are combustion reactions that don't give that, but they do produce usually heat, energy, or light. And those are the ones that sometimes are a little bit difficult to balance, okay, but they do balance. If I don't have enough energy or enough oxygen, I don't know why that fire didn't want to go away. So this, I don't think I can move it, nope. So incomplete combustion is when I don't have enough oxygen. If I don't have enough oxygen, I get CO along with CO2. And that's where we have problems in the wintertime when the heaters come on. Some of the things that happen, you get headaches, nausea, dizziness, breathlessness, collapsing, and then loss of consciousness. So it starts feeling like you got the flu, but then you also get this breathlessness and dizziness, and then you collapse if you stay too long in there. Okay, and then we get to redox reactions. So this redox and non-redox are way up here, above these other types of reactions that we've talked about. A redox reaction, the elements change the charge that they have from one side of the reaction to the other side. So if they change the charge, they have to be elements that can change charge. So usually we're not, if we're working with a metal, it's got to be able to change charge. So that's either gaining electrons or losing electrons. Oxidation is loss of electrons, becoming skinnier. Reduction is gaining electrons, becoming more negative because they're getting bigger. So you like my little visual. Oxidation number is that charge, is basically the charge on the element. Oxidation state, same thing as oxidation number. A non-redox reaction would say the same, the element would say the same on charge from side to side. So if sodium is a +1 on one side of the reaction, it's still a +1 on the other side of the reaction, that's not redox. Redox would be like sodium metal, which doesn't have a charge, going to sodium ion, which does have a charge. Did you get a packet? Okay. This. Okay. You should be with us. All right, you ready to move forward? Okay. So, easy way to remember it. Leo the lion says GER. Loss of electrons is oxidation. GER, gain of electrons is reduction. Or you can do oil rig. Oxidation is loss, reduction is gain. However you want to remember it, this is just a tool to help you remember which one's which. Okay? So, in oxidation states we have some rules. The first rule is any element by itself is 0. That includes Braunhilfe. Okay, and phosphorus and sulfur when they're by themselves, but they're not by themselves because they're part of a twin or part of a quad. Second rule is fluorine is always -1. Doesn't take a different charge, it's always -1. The third rule, groups 1 and 2 have a +1 and a +2, respectively, with the exception of hydrogen, which can be forced to be a -1 when combined with any element that has one specific charge. So that's any element in columns 1 or 2 or the slide. Okay? It can be forced to be a -1. It doesn't like that, but it will do it. So these are just basic rules. If you know these rules, you can figure out any other oxidation state or charge. Okay? Going forward just a little bit. We okay? Fourth one, oxidation state of oxygen is -2 except when it's forced to be a -1 in peroxides. That's like H2O2 or Li2O2 or Na2O2. Those are the most common ones. Aluminum, boron, and gallium are always +3. That's part of our slide. Algebraically, the sum of a compound must always equal 0 unless it has a charge on it in the equation. Okay? And the algebraic sum of polyatomics must always equal their charge. So if I have PO4 and it's -3, then each of the ions need to add up to -3. All right, so let's use these. Breaking it down. What do we know for sure? Sodium's in column 1, right? I have 3 of them. Sodium is a +1 charge. I know that. Plus, do we have a rule for phosphorus? No. It's going to be my X. Plus, I have 4 oxygens. Do we have a rule for oxygen? Yes, it's -2. I know this all has to equal 0. So I can quickly say, 3 plus X minus 8 equals 0. Well, 3 minus 8 will be -5, right? So X equals 5. So we're doing a little algebra. Okay, that means this has a +5, this has a +1, and this is -2. All right, over here, we don't know sulfur, so sulfur is our X, plus 4 times oxygen, which is -2. This has to equal a -2 because it has to equal the charge. Okay, so we have X minus 8 equals -2. Well, if I add 8 to both sides, then I have X equals a +6. So sulfur is a +6, oxygen's a -2. So I need to be able to look at each of these and figure out what the charge is. So I'm not going to go through all of them, but go ahead and finish the ones on this right here. We'll stop right here and see how you did. Okay, we've got about 2 or 3 minutes. I might pull you a few of you up to put those up on the board. Or I might do them real slowly. See if you can catch up with me. Okay, I'll have to write them up on later. See what you can do with them. We'll come back and trade, see what's going on.